everyone, and welcome to the CP-31 Sheet solutions for the 1600 rated problems. I'm Vibhaas Srivastava, and today we'll be discussing problem 12, interesting sequence. So let's go ahead and pull up the problem. So let's go to the 3P31 sheet and open up the problem. Okay, so Petya and his friend like to solve exciting math problems. One day, Petya came up with the numbers n and x and wrote the following equality on the board. N and n plus 1 and so on up till m is equal to x. Then he asked his friend Petya, find the smallest m such that this equality holds. Now, you're expected to solve this problem, and n and x goes up to 10 power 8, 10 power 18. So we can write that here. So n and x less than equal to 10 power 18. And what we need to find here is basically the smallest m, the smallest m, the smallest m such that uh, n and n plus 1 and so on m is equal to x, right? And it's pretty straightforward, like question. There's not much confusing in the question, but obviously knowing how to solve it is a different matter. But the question itself is pretty straightforward and mathematical. So let's dive right in. We know that n and x go up to 10 power 80. So obviously the expected time complexity would be something along, log n, um, log square, and right, something like that will work. But obviously, big O of n solutions will obviously not work, right? We need to figure out some way to. Even big O of square root n will also not work, right? Big O of square root n will also not work. We need to figure out some better way to do it. Okay, so let's have a look at what that can be. Um, let's try some examples. So let's try the first example. Let's try the first example. Um, 10 and 8, right? So we can go ahead and start doing ANDs. So 10 itself, if you take the AND, is equal to 10. Now 10 and 11, this value is equal to, so if you write the binary representation, you have 10 like this, and you have 11 like this, right? And if you take AND, this will still be equal to 10. Now what about 10 and 11 and 12, right? So this is going to be simply 10 and 12, right? So it's going to be this value. And when you take AND, as you can see, AND of these two values becomes 8. So that's why our answer is m equals 8, m equals 12, right? Because the first value of m such that this held true was 12. Okay. So basically what we have seen is that first of all, when you take AND, right? So let's start making observations. From this example, one observation we can have is that our target x, our target x, it must be some like some subset, must have some subset of bits of n, right? Because whatever the bits of n are, when we do n and n plus 1 and n plus 2, so on, then the bits are only diminishing. There are no new bits being formed, right? So since the bits are only diminishing, we can say that, like, if n had some bits, let's say n was equal to this number, right? And let's say if x has some bits, something like this, and as you can see here, x has one additional bit, right? It has an additional bit over here. So basically, if there is some additional bit like this, we can say that it's not possible, and we can directly output -1, right? So this is one observation we can make. Okay, so now we need to find out which number becomes equal to our target, right? So here, obviously, it's a bitwise question. So we should try to think of the numbers in terms of binary values. So let's just write down some binary number. Okay, assume n is equal to some binary number like this. So now we need to find um, when is the first instance it becomes equal to this binary number. Okay. Now, one more observation we can make is that um, whatever your target value of x is, it is going to be not only some subset of n, but it's also going to be a subset of the bits of n, such that some prefix has become 0. Okay, so we can observe that some prefix has become zeros. Otherwise, like for example, let's say we have um, n equals 1100 and x equals 0100, right? And this will not be possible because when you increment from n, when you increment from n, the numbers we get are of this following form, right? 1110, then 1111, right? And we get, let's say, 1000, right? So basically, what is happening is the smaller bits, right? The smaller bits, they will turn off first during the AND, right? The smaller bits will turn off first during the AND rather than the larger bits, right? Rather than the larger bits, the smaller bits are going to be the ones which will turn off first rather than the larger bits. That's why we are having some prefix of it become 0. So we'll get more deep into this with another example. So let's just take another example. Let's say we had a number like this, okay? And so as you increment n, so let's just see what happens when you increment n, right? So as you increment n, we get this following number, and then the next number which we get is this one, and then the next number which we get is this one, right? So as you can see over here, all the bits are equal to the bits of n. Here, this first bit gets flipped, right? This first bit becomes a 0. So the AND at this position becomes a 0 from this point forwards, right? So first the smallest bit changes and the remaining bits are the same, right? Then this bit changes, right? And then finally, after some time, this bit will change. And then later, finally, this bit will change and AND will become 0, right? So basically, the value of AND will turn off the value of bits of in the AND of bits in the AND will turn to 0 first for the smaller bits, first for the smaller or LSB, like least significant bits, and later for the larger or more significant bits. Okay, later for MSB. And the way this pattern goes is eventually the AND will become 0, right? Eventually the AND is going to become 0. So even if you take this example, here the AND is equal to this, right? So this is our N and this is our current AND. Okay. So then if you have N plus 1, we get something like this. If you take AND, then one bit has vanished, right? This bit has vanished. Now if you keep going, we get this. The AND is still equal to the same value right now, AND did not change. Then if you do N plus 3, we get this value, right? And then the AND, this bit also vanishes in the AND, right? So this bit also vanishes in the AND. So basically the AND gets smaller, right? The AND gets smaller, the larger the number becomes, the smaller the AND will get, and the bits will get removed from the right to left. Basically, the least significant bit to the most significant bit is getting removed, right? So one more thing we have to ensure is that, um, one more thing we can ensure is that basically the target value x has to be equal to our value n, except some prefix of it is turned into zeros. Okay, so let's write down our second observation, and it is basically our target and value x can only be some sub mask, you could say some sub mask of n where some prefix, some prefix means MSBs, sorry, LSBs, right? Prefix means LSBs, uh, have been turned into zero, have turned to zero. Okay, so now this gives us a strategy for finding out which exactly prefixes have been turned to zero, right? So one way we can do this is we can find out how much exactly is the prefix which we are turning to zero. So for example, um, let's say we're given a number like this, right? This is our n, and we're given a target x, which is equal to, let's say, this value, okay, equal to this value. Then basically what we have done is this whole portion, right? This whole portion has been converted, this prefix has turned to zero, right? So we can say that this x is obviously valid, but we need to figure out what is the smallest m that will convert all of these to zero. All right. So basically, how can we find out the smallest prefix? What we can say is, we can say that this is a shift of 1, 2, 3, 4, 5, 6, 7, right? Shift of 7. So basically, if we take n and then right shift it by 7 and then left shift it back to 7, right? This is equal to x, right? So in general, we can write, in general, we can write n right shifted by I, left shifted by I again. If this is equal to x, right, then we know that the the I prefix values, basically prefix values, have been turned to zero, have been turned to zero, and we need to find the smallest such m which does this. All right, so and we need to find the smallest m, right? So we have found how much shift is needed, but now we just need to find the smallest m, and that is also pretty mathematically evident if you're familiar with like basic number system ideas, basic bit bit ideas. Let's take this example itself, right? Very similar example, and we're trying to make it equal to this x, right? We're trying to make it equal to this x. Now, when will this x occur for the smallest term, right? When will this x occur for the smallest term? Well, obviously, when you increase this number, first, if you add one, okay, if you do n plus one, then what happens is basically this bit becomes a one, right? So this bit becomes a one, right? Then if you add another one, this will become a zero. Sorry, this bit becomes a one. So then this bit will become a one and all of these will flip to zeros, right? So this is what happens when you add one. Now if you add one again, this becomes one, add one again, and then what we have is we have um, 1, 0, right? And add another one, this becomes 1, 1, and so on, it starts counting up, right? So as slowly as it counts up, it will reach a number which looks like this, right? It's going to reach a number which looks like this. And when you finally add one last time, right? When you add one last time, then basically it becomes this, right? It becomes some number like this, which finally is going to be our m, right? So if you do n and n plus 1 and n plus 2 all the way to this number, right? All the way to this number m, then and only then we can get our target, right? And how do we find this m? Basically, we can say that this m is simply our n itself when we right shifted by I, left shifted by I, and then this happens at position 2 to the power I, right? The position 1 left shifted by I, so or 1 left shifted by I, right? So this is the number, this is the value of m. Okay, this is the value of m. However, we need to pay attention that this value of m um, might not always work. So for example, let me just give you an example. So we have an example, and I'll show you the n is equal to 7, x is equal to 3. Okay, and so if you write down 7, it looks like this in binary. Sorry, x is equal to 6, right? If you write down 6, this is equal to this in binary. Now the thing is, as soon as you do 7 and 7 plus 1, which is 8, right? So you get immediately 0 because 8 is equal to 1, 0, 0, 0, right? You immediately get 0 and you will never get 6, right? Here the and is 7, here the and is 0. You will never get 6. And basically this is failing is because when you do this process, you right shift 7 by 2 places and left shift it again, right? So basically when you do and, you get the number 6 back, right? You get the number 6 back. You get m equals 6 basically. And m cannot be less than n, right? M must always be greater than equal to n. So in that case, if m is less than n, then obviously it is not possible, right? If m is less than n, it is not possible. And what is m? M is defined to be this value. Uh, M is defined to be this value over here, right? N right shifted by I, left shifted by I, or 1 left shifted by I. So M is equal to N right shifted by I, left shifted by I. So basically we're erasing those zeros, and then the next one we are turning it on, right? The next one we are turning it on, right? So if this number is lesser than n, then it's obviously not possible. Otherwise, it is possible, and this is the m, right? And that's all. The way the shifts have written, you can do a brute force in the way you want to find the exact shift amount, right? So first we'll try I equals 1, I equals 0, then I equals 1, so on till I equals roughly 62 because 10 to the power 18. If you take log, it is roughly, I think, 60 or 61, right? If you take log base 2 of 10 power 18. So the time complexity of this is also log n, right? The time complexity of this method is big O of log n per input, right? And its memory complexity will be big O of 1 because we're not storing any array or any such thing. So yeah, let's have a quick look at the code. Our final solution, let me just write it down. So basically our solution is going to be like, for each possible shift, for each possible like prefix which we are deleting, right? Deleted prefix, right? So each possible deleted prefix from basically I equals 0 to I equals 62. What we'll do is first we'll check if um, this value, right? The n right shifted by left shifted by is equal to x, right? If this is equal to x, if this is equal to x, we'll find our m as this value or 1 left shifted by I, right? And then if m is less than n, minus 1, otherwise answer is equal to n, right? So this is basically the solution. It's a purely mathematical problem, at least based like if you think about the numbers in bitwise and if you think about how numbers get added in bitwise, a purely simple mathematical problem trying to find which number it is, right? Let's have a quick look at the code. There are some implementation details which must be kept in mind. So here we are with the code. Right. As you can see, its time complexity is log n, memory complexity is big of 1, right? We're taking input nx. So here I've kept a special case for n equal to x. In that case, we know obviously the answer is just n itself. And this case I've kept because a shift of 0, right? A shift of 0 is a bit hard to represent. That's why I just kept this case separately. Depending on how you write this logic, you could not keep this case as well. So initially the answer is set as -1. If we find some I, so we're going through all possible shifts to remove the prefix, right? If we find some I, which if we remove, it becomes equal to x, then we know m. So m is basically what I've stored in val, right? So if the val is greater than equal to n, that's going to be our answer. Otherwise, our answer will be -1. And then we can break, right? And we can output the answer. And that's all. This runs pretty fast, just in log n with memory complexity of big O of 1. And it clears all test cases within 100 milliseconds. So if you had any trouble with this problem, you should definitely practice some bitwise operators, right? Practice some thinking in the logic of bits. So yeah, that's all for this problem. Thank you and see you in the next solution.